In this video, we're going to be analysing the summing amplifier. So that's the kind of circuit that we can see in the middle of the screen here. You can see that we have an op-amp, and once again we'll assume an ideal op-amp here with an infinite gain, infinite open loop gain that is. And we have it in the inverting amplifier configuration in that the non-inverting input is going directly to ground, and we have a feedback resistor from the output to the inverting input. But instead of having a single input signal and a single input resistor here, we have three different input lines all in parallel. And you see the bottom line here is labeled Rn, so this is indicating that this could go on indefinitely. You could have 4 input lines, 5 input lines, however many you want. So what we're interested in finding out at this point is what is the output equation, the transfer function of this op-amp? What is Vout for any given input voltages? So we begin the analysis by once again recognizing that if we have an ideal op-amp of A equal to infinity, then we have a virtual short, which is in effect a virtual ground between our inverting inputs, due to the fact that the op-amp by itself leads to this output characteristic. So for more details on this particular step, you can look back at the ideal inverting op-amp configuration video. So if we know we have a virtual ground, then we know that not only is V2 at 0 volts, but V1 is also at 0 volts. And the next step is to simply apply Kirchhoff's current law. So we have several currents in this circuit. Let's call this main one just I. But over here we have I1, we have I2, and we have IN. Now, as we know from our ideal op-amp characteristics of the infinite input impedance, there can be no current flowing into the input terminals of the op-amp. So from Kirchhoff's current laws, we can straight away say that our main current going through the feedback resistor I is going to be equal to I1 plus I2 plus IN. Now if we know our current for I, then we can work out Vout, because we know that V1 is 0, know that our Vout is going to be equal to 0 minus RFI, that being the voltage dropped across the feedback resistor. So therefore Vout really just equals minus RFI. So to work out the value of the current going through the feedback resistor RF, so to work out this I, we can apply superposition. And that's because our circuit's made up of just linear components, all of these different resistors. And whilst we do have a non-linear component in the op-amp here, we're treating it under the ideal op-amp assumptions, and therefore using its kind of equivalent circuit and maintaining linearity within our circuit. Now before we proceed, we'll just note that through conventional notation of the op-amp inputs, we have two V1s. So we'll just label this one V1 minus for clarity. So when using superposition, to find out the current of interest, you simply ground the other inputs. So if we want to know the current I1, then that's simply going to be V1 minus the voltage going into the inverting op-amp input, so that's the V1 minus, all over R1. And we know that the V1 minus is 0, so this just equals V1 over R1. And that's because we can simply ignore V2 and Vn in this circumstance because we're just grounding those inputs based on superposition. Using the same approach, if we want to find I2, we'll get the answer of V2 over R2. And in that case, the V1 and the Vn inputs are grounded. And of course, to finish, In will equal Vn over Rn. So when we combine this with the fact that we already know that our total I is equal to I1 plus I2 plus In, then we can easily work out our output voltage as Vout equals minus Rf I, which equals minus Rf V1 over R1 plus V2 over R2 plus Vn over Rn. So that's our expression for the output voltage of our summing amplifier. And so of course at this stage you can see why we called it a summing amplifier. If we take the example up in the top right here, if we say that R1 equals R2 equals Rn equals Rf, let's say all equal to 1k. If we were to plug those 1k values into the Vout equation, then we can see that Vout will simply equal V1 plus V2 plus Vn. So our output voltage is simply the sum of the 3 different input voltages, or however many different inputs we have in this configuration. Now, we can know from our inverting amplifier analysis previously, and from our output equation here, that if we adjust our RF, or the ratio of RF to R1 or ratio of RF to R2, you'll change the gain of the circuit. So you could have the Vout being some multiplication of the sum of the different inputs. And by changing R1, R2 and Rn relative to each other, you'll change the weight of that particular input voltage. So you could give more weight to V1 by adjusting the value of R1 relative to R2 and Rn. So this has a lot of different options and a lot of configurations and ways it can be set up depending on your purpose. But for this simple analysis, you can see how it results in these added voltages, and hence why it's called the summing amplifier.